तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This is the 22nd lecture of this course and the 4th lecture on PN junction. So far we have completed the equilibrium analysis of the junction. With this we are ready to explain the static current voltage characteristics. So we will begin by explaining the characteristics shown on this slide. So these are the forward current voltage characteristics. This is what we will try to explain to start with. Now the methodology adopted will be the same as that outlined in the device modeling procedure. Let us look at that procedure once more so that we recapitulate the steps involved in device analysis. This is shown on this slide. The same set of approximations may not hold over the entire device volume. Hence, partition the device into different regions. Now, let us see equilibrium analysis. What has it told us about the partitioning of the device? So, the device is partitioned into 3 regions. So, this XD is the space charge region, and these two are the so called neutral regions. So we are partitioning the device into space charge and neutral regions. So this is the first step in the analysis, and this has already been achieved in the equilibrium analysis. What is important to see now is how this regions, the width of the regions is affected when you apply a forward bias. Let us look at the next step in device analysis as shown on this slide. Analyze each region using a suitable set of approximations and boundary conditions to obtain N, P, Jn, Jp and E in that region. Approximations for different regions can be different. So the regions that we considered, that is the space charge and neutral regions, will be analyzed using different set of approximations. Now that is why what we do here is that we create a table like this, wherein we list the various equations, transport equation, continuity equation and Gauss's law, and we list the approximations for these equations in the space charge region and in the quasi neutral region. So these approximations are likely to be different because of the differing physical conditions in these regions. So this is the approximations table. The next step, as shown on the slide, is combine the information regarding N, P, Jn, Jp and E obtained in different regions, ensuring continuity of these parameters across the boundaries separating the regions to obtain the complete picture. So that is the outline of the approach that we are going to adopt to derive the current voltage characteristics. Now I want to emphasize the fact that first we will do the analysis with the help of the 5 basic equations without using the energy band diagram, and then after completing the analysis we will discuss the energy band diagram under applied bias conditions. So let us list what are the assumptions that we are going to make, that is the simplifying assumptions. The characteristics that are obtained under these set of assumptions are called the ideal IV characteristics. So first we derive ideal IV characteristics based on a large number of assumptions, and then we discuss how some of the assumptions have to be relaxed to get the real characteristics which were shown on this slide. So some of the assumptions which we have already made, let me recapitulate: that the boundary between the space charge and neutral region as shown by these lines is abrupt, the junction itself is abrupt, the p and n regions are uniformly doped, and the widths of these regions are much more than the diffusion lengths. That is, this width of the p region is much greater than the diffusion length of electrons, and this width of the n region is much greater than the diffusion length of holes here. What are the additional assumptions we will make? The one important assumption we will make is that the applied forward bias is really very small, so that the equilibrium conditions are disturbed only to a small extent. This is the so called important quasi equilibrium approximation. So this is one important approximation that we are going to make, quasi equilibrium. Next, the applied voltage drops across the neutral regions as well as the space charge region. So let us show these different voltage drops as Vp across the p region, Vd across the space charge or depletion region, and Vn across the neutral n region. Now these two regions which are neutral under equilibrium will continue to be approximately so under applied bias. That is why these two regions are referred to as quasi neutral regions. So in our table here, that is why we have listed the p and n regions as quasi neutral regions. So returning to the voltages, here what we will do is we will neglect Vp and Vn and we will assume that they are much less than Vd, so that this Vd is approximately equal to the applied voltage. So we are assuming that the entire applied voltage falls across the depletion layer. This is the next important assumption. V is approximately equal to Vd, which is much greater than Vp or Vn. Now how do we analyze the diode under these assumptions? So let us look at the space charge region first. Let us draw the electric field in the space charge region under the applied small forward voltage. For this purpose, we will make the depletion approximation. We have already shown that the depletion approximation is valid under equilibrium conditions. We can easily show that it will continue to be valid under applied bias also. This is because if you write the space charge equation, rho is given by q times p minus n plus Nd minus Na. We are assuming complete ionization of the impurities. Under equilibrium conditions, this P is equal to P naught and N is equal to N naught, and in the space charge layer, this P naught minus N naught we have said can be neglected. That is a depletion approximation. Now under non-equilibrium conditions, what happens is this P naught minus N naught becomes P minus N, and which can be written as P naught plus delta P minus N naught plus delta n. That is, under applied bias you have excess carriers delta p and delta n, which is nothing but p naught minus n naught plus delta p minus delta n. Now we already have shown that this quantity can be neglected, because under equilibrium conditions the depletion approximation is valid. Now under applied bias, since delta p is approximately equal to delta n, that is, electrons and holes are generated in pairs, therefore this quantity also will be close to 0 and this can be neglected, and that is why the depletion approximation is also valid even in the presence of excess carriers, okay, in the space charge region. So based on the depletion approximation, if you plot the electric field picture, then it can be drawn as follows. So you draw two linear segments. Now what is the width of the space charge region? How do you determine the width under applied bias? For this purpose, note that a voltage of V volts is coming across the space charge layer. We are assuming that the V applied voltage falls entirely across the depletion layer. This is the assumption that we are making. So that is why the voltage comes across this space charge layer, and you can see the electric field because of this voltage is in this direction from P to N, and this electric field is superposed on already existing electric field in the depletion layer. That is a built-in electric field that is in the opposite direction, directed from N to P, because you have positively charged donors here and negatively charged acceptors here, which are causing the electric field. Now this is the built-in electric field, and this is the externally applied electric field because of the voltage. Notice that externally applied electric field has been shown by a shorter arrow as compared to the built-in electric field. This is because we have shown that the electric field under equilibrium conditions is very high, and we also said that we are assuming quasi-equilibrium conditions wherein the applied voltage is very small. Now how small should this applied voltage be? This will become clear by the end of the analysis. So the superposition of this over this would mean that the electric field will remain in this direction even under applied bias, but it will reduce in magnitude. So if you want to show this by an arrow, if this is the built-in electric field and this is the external electric field, then this is the electric field under applied bias within the space charge layer. In other words, the electric field has reduced everywhere. This is logical because now the voltage drop across the space charge layer would be the built-in voltage drop which was there under equilibrium conditions, that is psi naught, which was directed in this way, minus the externally applied voltage, that is V. So the area under this picture, the field picture, so this is E versus X, this area is psi naught minus V. It was psi naught under equilibrium conditions. When you apply an external bias, forward bias, which means the bias is polarity is positive on P side and negative on N side, it opposes the equilibrium conditions and therefore it subtracts from the equilibrium voltage or the psi naught. So that is the area under this curve, that is the voltage across the space charge layer under forward bias. Now we can determine the new depletion width, assuming this voltage drop and the depletion approximation, and the formula for this will be exactly the same as that we have written under equilibrium conditions, except that the built-in voltage psi naught should be replaced by psi naught minus V. So if you do that exercise, our depletion width expression would be xd is equal to square root of 2 epsilon psi naught minus v upon q into 1 by Na plus 1 by Nd. So this clearly shows that because this voltage has reduced by V, your depletion width has reduced. So let us list this approximation that we have made. That is the depletion approximation in the space charge layer. And this approximation will be listed against the Gauss's law. So far now we have used first the Gauss's law of all these equations to determine the reduction in the space charge region width under forward bias. So here we make the entry depletion approximation. So if we show now on this diagram the equilibrium conditions for comparison, then the equilibrium electric field picture can be shown by this dotted line. So that is your, from this end to the other end is the equilibrium depletion width, and this end to the other end here for the solid line is the new electric field, new depletion width. Okay, so that completes the analysis related to the width of the depletion region. Next, let us try to plot the electron and hole concentrations under applied bias conditions. So since we are showing both the electron and the hole concentrations, we must show them on a log scale. Now to begin with, let us see how we had sketched the variations of N and P under equilibrium. So I am first going to show, for the purpose of reference, the equilibrium variation of holes and electrons. This will be done by a dotted line. So the hole concentration is majority carriers here, and then it varies like this, and here it is a minority carrier concentration. So this is PP0 and this is PN0. To avoid cluttering in the diagram, I am not showing the electron concentration variation. We will show how, starting from this kind of variation of the hole concentration under equilibrium conditions, we can sketch the variation of the hole concentration under applied forward bias, and then one can do a similar thing for the electrons also. Now here notice that the concentrations at these two edges of the depletion layer were related to the potential drop between these 2 points by the Boltzmann relation. So which said that the potential drop between the edges of the depletion layer, which is psi naught, is equal to Vt into ln of Pp0 hole concentration on P side by Pn0, that is the whole concentration on the N side. This Boltzmann relation was obtained using the equilibrium condition that Jn equal to 0 and Jp equal to 0. That is the reason. The reason for this is that the drift and diffusion currents were in balance. Now we have estimated the average values of diffusion currents for holes and electrons, and we found that the values were rather large. If you look at the values that we had obtained from the equilibrium analysis for average diffusion current of holes it was around couple of 100 amperes per centimeter square, the current density. And for electrons, the diffusion, average diffusion current under equilibrium over the space charge region was more than 50 amperes per centimeter square. So these are really very large currents. In practice, if you were to estimate the forward current through a diode under quasi-equilibrium conditions, that is for small applied voltages, then the current densities would be much less than ampere per centimeter square values. Okay? And therefore, what we can say is that under applied bias, Jn will continue to be approximately equal to 0, though not exactly equal to 0, and similarly Jp will continue to be approximately equal to 0. This is the statement of quasi-equilibrium. So statement of equilibrium is that these are exactly equal, and statement of quasi-equilibrium is that these are approximately equal. Now, why is there a small difference between the drift and diffusion components of Jn and similar components of Jp? This is because now you can see that the applied bias is in this direction, so the electric field is reduced as compared to equilibrium conditions. This is the built-in electric field, and this is the field under applied bias, E under forward bias, for example, in this case. Now, since this electric field has reduced, as can be seen from here also, okay, so this is equilibrium, the dotted line is equilibrium. Therefore, the drift component of the currents would have reduced as compared to equilibrium. So this is why the diffusion component of the currents across the space charge layer would dominate over the drift current. Okay, and that is why the diffusion and drift currents are slightly in imbalance, and it is this imbalance that gives rise to the resultant current. But since this resultant current, which is the difference of drift and diffusion components, is very small compared to individual drift and diffusion components, therefore the drift and diffusion components can be assumed to be approximately equal. Okay, we have explained this very clearly in the topic on device analysis procedure. So what is the meaning of quasi-equilibrium? When the currents, drift and diffusion are very high and they are in approximate balance. This has already been explained. So I am only recapitulating for your convenience. So this is the assumptions, this is a very important assumption that we are going to make to get the carrier concentrations for electrons and holes in the depletion layer under applied bias conditions. So let us list that assumption here. So transport equations, the assumption you are making is Jn approximately equal to 0. That is to say, Jn drift and Jn diffusion are approximately in balance, because the difference between these two is very small, and a similar thing follows for Jp. So you can write a similar thing for holes here. Okay, so that is Jp drift is approximately equal to Jp diffusion. So using these approximations, now if Jp equal to 0 leads to this condition, then Jp approximately equal to 0 will lead to a similar condition, that now the new voltage drop is psi naught minus V, left hand side is psi naught minus V under applied bias. So let us write it clearly. forward bias, Jp approximately equal to 0, which means the left hand side is psi naught minus V is approximately equal to, the right hand side is Vt ln, now Pp0 will change to Pp and Pn0 will change to Pn, that is the non-equilibrium values. Now what is going to happen is that since the ratio is decreasing, this Pp by Pn is decreasing, it definitely means that the Pn is increasing, okay, that is holes are being injected from P plus region to N region. Because of this applied forward voltage, this is the polarity of the voltage, as we explained in our simple qualitative analysis, that the negative terminal will attract holes. So the negative terminal will attract holes from here, from P region, therefore holes are being injected into N region, therefore concentration of holes in N region increases, that is why the Pn will increase. Now what about Pp? Well, it can be shown that Pp will also increase, because just as holes are injected from P to N, because of this negative potential here, the positive potential here attracts electrons from N region into P region. So electrons will be injected from N to P. This means the electron concentration will increase on the P region. But since these two regions, which are not space charged regions, which are quasi neutral regions, there any excess electrons should be counterbalanced by excess holes, otherwise the neutrality will not be maintained. Therefore, if you have excess electrons injected into this region from the N side, excess holes will also appear here to compensate the excess electrons from the positive contact. So in fact this can be shown very nicely using a flow diagram. The flow diagram will be that the contact injects holes so the N region is injecting electrons. Let us say the dotted line indicates electrons. Now because this is quasi neutral region, holes are injected from the contact. Now we have already said that holes are also injected into the N region, because they are attracted to the negative potential here. So this terminal here provides holes to compensate for excess electrons and also for injection into the N side. And similarly, since there are excess holes here and this region is quasi neutral, excess electrons will appear in this region to compensate for charges from the electrons from the negative contact, and therefore you have electrons injected from the contact, so from this terminal. So this is how you have E minus injected here, okay. So the terminal injects electrons to compensate for holes here, and it also injects electrons into this region, into the P region. So this is the flow diagram. Now the net effect of this flow diagram is that you have excess electrons and holes in both neutral P and neutral N regions. So we can show this picture as follows. So quasi neutral P region, because of injection of electrons, Np0 changes to Np0 plus delta n. To compensate for this delta n, your pp0 will also change to pp0 plus delta n. So the whole concentration is also increasing in the p region by the same concentration as injected electrons. So these delta n injected electrons are these electrons here, which are equal to this delta p holes. Now what is happening? What does this arrow indicate here? This arrow indicates that the excess holes and electrons are recombining. So and they are continuously being replenished by the contacts. So when you apply forward bias, electrons are continuously injected from n to p region. Terminal is also injecting holes to compensate for the electrons, and the electrons and holes recombine. And of course holes are also being continuously injected here, and these are again compensated by electrons here, okay, and these are recombining. That is how the current is maintained. So these are injected electrons, and these are the concentration of holes to compensate for this electrons. So though we write delta n here, it is to be understood that this indicates the excess holes, okay, which are compensating for this. The magnitude of these excess holes is exactly delta n in this region. So in n region, similarly, one can write the Pn0, the minority hole concentration gets changed because of injection of holes from p side to Pn0 plus delta p, and to keep charge neutrality, the majority electron concentration also changes from Nn0 to Nn0 plus an excess electron concentration, which is equal to this injected hole concentration. Thus, if you want to write this ratio pp by pn, we can write it as pp by pn equal to pp0 plus delta n by pn0 plus delta p. Now it is important to note that this pp and pn correspond to the depletion edges, okay. So in other words, pp is the value of hole concentration here, and pn is the value of hole concentration at this edge. Let us show pn, so something like this at the depletion edge. Now what about pp? pp is pp0 plus delta n. Now this is where we make an important assumption, that is the low injection level assumption. So this is an additional assumption for the ideal IV characteristics. According to low level assumption, the majority carrier concentration is not disturbed because of injection of electrons or holes, both on the p side as well as on the n side. So low level assumption means that pp, which is equal to pp0 plus delta n, is approximately equal to pp0 even under applied bias, okay. So this delta n is much less than pp0. This is the meaning of low level conditions. Similar arguments will apply also to electrons, but since we are considering holes, let us write here the result. This is approximately equal to pp0 upon pn0 plus delta p. where it is important to note that this delta P is a value at the depletion edge. So what we will do is we will use the symbol capital delta to indicate values at the depletion edge. So delta P at depletion edge in the N region is equal to capital delta P, so that we can retain delta P symbol to show the value of excess hole concentration at any x. Similarly, delta N at the depletion edge in the P region will be delta N. Okay. So with this symbolism we can replace this delta N by capital delta N and this by capital delta P and this by capital delta P. So in other words, this difference here is capital delta P. Now PP0 plus delta N is approximately equal to PP0. That is the consequence of low level assumption, which means that even under applied bias on a log scale the majority carrier concentration will not be disturbed. So this part, this particular fact we have emphasized in our discussion on excess carriers, that low level conditions means that when you plot majority and minority carrier concentration on a log scale, the majority carrier concentration appears undisturbed, whereas the minority carrier concentration however is definitely disturbed. So based on these arguments one can plot the hole concentration under low level at forward bias as follows, something like this within the depletion layer and on this side. So we will list the assumption that we are making here. In the space charge region we are assuming that low level assumption prevails. So let us list it here. And since we will assume low level conditions everywhere, strictly speaking this low level assumption should be listed in quasi neutral region, because only there you have high concentration of majority carriers and low concentration of minority carriers. In the depletion layer the carrier concentration really does not exist, so we must list it under quasi neutral region and not under space charge region. Now let us return to this particular equation. What does it tell us about the value of delta P? So we write psi naught minus V is approximately equal to Vt ln Pp0 by Pn0 plus delta P. Now we already know that psi naught is Vt ln Pp0 by Pn0. Therefore we can subtract this equation from this equation and we can write V is approximately equal to Vt ln, we are subtracting this from this, so you get Pn0 plus delta P upon Pn0. So in other words, you can transform this equation and you will get delta P is approximately given by Pn0 into exponential of V by Vt minus 1. So this is the important result that we get from the Boltzmann relation under applied forward bias. So excess hole concentration on the n side, this is on the n side, that is excess minority carrier concentration on the n side increases exponentially with respect to voltage, and in fact as we will see, it is this exponential increase of the concentration that is responsible for the exponential nature of the current voltage characteristics. You know that current is proportional to the excess carrier concentration. So if excess carrier concentration increases exponentially with voltage, current will also increase exponentially with voltage. Okay. So with that we have completed the analysis in the space charge region for the concentrations of holes and electrons. Though we have not drawn for electrons, you can draw a similar curve for electrons yourself. Now what is the next step in the analysis? Now we must move to the quasi-neutral region, because we would like to know how this hole concentration which we have seen up to this point here, how this will vary in this region, and of course analogously how the electron concentration would vary in the quasi-neutral P region. Now to move here in this region, we need to use an approximation that has been pointed out earlier, and that is that we assume that since we are considering minority carriers, okay, note that the whole concentration on n side here is minority carrier concentration. So these holes which will move towards the contact in the n region, they will move by the process of diffusion. So even though electric field may be present, the field would be really very small, okay, it will not cause any significant drift current for minority carriers. So we make the very important diffusion approximation for minority carriers. So let us list this approximation here. So for in transport equations in quasi-neutral region, you have the diffusion approximation for minority carriers. And a consequence of diffusion approximation for minority carriers is that for the continuity equation you can use the diffusion equation right, diffusion continuity equation for minority carriers. And we know that the solution of the diffusion continuity equation is an exponential. So this part also was very clearly pointed out in the procedure for device analysis. In other words, therefore, we can say that beyond this point the whole concentration would decay exponentially to the equilibrium value. Please note that we have assumed this region to be very, very long, the n region to be very, very long. So long as compared to the minority carrier diffusion length. So now you will appreciate why we assume the quasi-neutral regions to be very long compared to the minority carrier diffusion lengths in the regions for ideal IV characteristics, okay, because the carriers here, the minority carriers are moving by diffusion, and therefore you get an exponential decay, and in the exponent you have the diffusion length of the minority carriers. So when you show that here, an exponential appears like a straight line, but as it approaches this equilibrium concentration, the straight line will saturate. So this is the kind of behavior you have. So in fact, to show this clearly, this behavior here clearly, we must go to the linear scale. Now on the linear scale, please note we cannot show both majority carrier concentrations and minority carrier concentrations. But fortunately, since we know that the disturbance in majority carrier concentration is almost equal to the disturbance in minority carrier concentration in the quasi-neutral regions, because quasi-neutrality has to be maintained. Therefore, we need not sketch the minority and majority carrier concentrations separately on a linear scale. So long as we sketch the excess carrier concentration on a linear scale, we know how the majority carrier concentration would change and how the minority carrier concentration would change. So we will sketch now the excess carrier concentration on a linear scale. So here, although the contact is shown here and this width is small, we must assume that this is sufficiently long. So we will redraw this neatly. And this is also assumed to be long enough. So what we will call this is delta P. Since this is n region, we plot excess minority carrier concentration. Okay, excess majority carrier concentration is equal to this. This is an exponential decay. Now note that I am not setting up any coordinate system here, okay, because that unnecessarily complicates matters. It is necessary to just realize that this shape is exponential. So this value here in this exponential decay, this value is delta P, that is capital delta P, which we have shown already is given by Pn0 exponential of V by Vt minus 1. And the nature of the exponential is shown by extending this line. The initial slope here, if you extend this, then this distance on the x-axis here is Lp, minority carrier diffusion length of holes. One can similarly show excess carrier concentration on the p side, and it would be like this. This is another exponential. Now notice that this excess electron concentration delta n at the depletion edge is shown less than the excess hole concentration delta P at this edge. This is because of this formula. Okay, so if you want to write here, this delta n is given by np0 exponential of V by Vt minus 1. Now since this is P plus, that is the doping on this side is more than the doping on this side, np0 will be less than Pn0. Minority carrier concentration on a heavily doped side is less as compared to the lightly doped side. That is why this is shown less as compared to this. Now with this we have completed the variation of the electron and hole concentrations with distance. Next, what is left is the current densities of electrons and holes. In fact, these current densities can now be very readily obtained from the variations of the minority carrier concentrations. So since we assume the diffusion approximation, we can sketch the concentrations of minority, we can sketch the current densities because of minority carriers from these two graphs. The current density for holes, for example in n region, is simply the slope of this, and the current density of electrons in this region is simply given by the slope of this shape of the curve. So let us draw that here. So this is the 0 line. Now the gradient is 0 here and it goes on increasing. So Jp will also be an exponential shape because the gradient of an exponential is an exponential. So this is Jp. In the n region. Similarly, Jn, the electron current will show by a dotted line. This is Jn. In the p region. So here we have used, please note, the diffusion approximation for minority carriers, which we have already listed here. Now, how do we complete this picture? If you want to get the total current, you know that J is equal to Jn plus Jp. So if I want to get the total current density, then at any point, any x, if I know Jp and Jn, I can get the total current. Unfortunately, with the picture that we have drawn, I do not know Jn in this region and I do not know Jp in this region, and I do not know either of them as of now in this region. So how do we proceed further? Now at this point I must tell you that since this is a steady state condition, J is constant with x. This we have shown as a consequence of steady state assumption in the procedure for device analysis. How? The total current because of Jn and Jp is constant with x. So that is why if we determine the total current at any x, we can determine the current injected at the contacts, because J will be drawn as a constant line here. It will be something like this, a constant line. Right now we do not know exactly where to draw. So to draw that, we will make an additional assumption, and that is that there is no change in the hole or electron currents in the depletion layer, which means there is no recombination of electrons and holes in the depletion layer. This is because the depletion layer is rather thin. We have seen that it is only about a micron. So we can assume the recombination to be negligible as an idealization. So this is equivalent to putting here the fact that dJp by dx and dJn by dx, the rate of change of the current densities with x is 0. This is equivalent to saying no recombination. In the space charge region. So now we draw two constant lines showing the variation of Jp and Jn in the space charge layer. Now moment we have done that, now you see that we obtain Jn and Jp both at this depletion edge as well as Jp and Jn both at this depletion edge because of extending these lines. And now therefore we know the total current, so I must add this and this to get the total current. So that is shown here. That will be the total current J everywhere. So this is how I have determined the total current J. I can easily write an expression for J based on this, because I know what is Jp here and I know what is Jn here. This Jp is, if you write in terms of this, the diffusion current at this edge. Please note that these two graphs are on the linear scale, okay, that is why you are able to show exponential variation as this shape. So this is Q dp into delta p upon Lp, the diffusion current at the depletion edge, that is obtained from this slope and the factor of diffusion approximation. Similarly, this current of electrons is q dn delta n upon ln. So we obtain therefore the equation for J as q times dp delta p upon lp plus dn delta n upon ln, where delta p is already written in terms of this formula. So if you simplify, that is you substitute this, it is very clearly seen that J is given by q into dp Pn0 upon Lp plus dn Np0 upon Ln multiplied by exponential of V by Vt minus 1. So this is the relation for the current, clearly showing the ideal current voltage characteristics given by J equal to a constant multiplied by exponential of V by Vt minus 1. So with this we come to the end of the present lecture, wherein we have used the 5 basic equations and stated the various approximations that need to be made in the space charge and neutral regions to arrive at the exponential ideal current voltage characteristics, or the ideal current voltage characteristics which are exponential in nature. We will continue with this analysis in the next class.